Hello everyone. Thank you for joining DataCon LA 2022. This is the last session. I know this has been tiring today. Welcome to Data for Good at last. My name is Reeti, your host, and we have our co-host today, Sadna and Nikhil. Don't hesitate to raise your hand if you have any questions, and please silence your phone during the session. This session has been recorded on Zoom, and the recording will be available in a few weeks. Today, we have our guest, Jason Kang, and he will be talking about Air Quality Analytic Center Framework. Jason came from computer science background with masters in computer science and data science. He has been with JPL for more than 10 years, mostly developing web-based applications. Most recently, he transitioned to a data engineer role that deals with Earth-related data science projects. He spends most of his time developing data pipelines and patching or improving data analytic platforms. Now, without further ado, I'll hand this over to the speaker. Thank you for being here, Jason.
Thank you so much. So today I will talk about the Air Quality Analytic Framework, also known as AQACF. Throughout this presentation, you will be forced to learn a bunch of acronyms. I apologize in advance. AQACF is a framework for it's a framework, also a platform to measure how atmospheric pollutants affect our air quality. Many people from different organizations have worked on this framework and this project. I'm not going to read them out one by one, but I do want to point out that Thomas Huang from JPL is the PI for this project. So if your organization is also interested in this kind of research, feel free to reach out to him. And I am also from JPL team as well. So when people hear about JPL, what immediately comes to mind is the Mars rover, the impressive Mars landing. People don't usually associate JPL with earth science, but in fact, that's something that we have been doing for the last 20, 30 years. For the planet we have studied so far, we have not found one that can sustain human life quite like Earth. Earth is a unique planet. It is plan A. We do not have a plan B right now. So Earth is our home. In order to protect our home, we need to understand it. And that is the motivation behind Earth science and ultimately behind this project. This project is funded by NASA Earth Science Technology Office through the Advanced Information System Technology Program, also known as AIST. Hence, you see the NASA AIST name at the bottom. The idea is to develop a collaborative analytic platform to support air quality research and application. Okay, so before we talk about the platform, I want to talk about the data sets. There are two types of data that go into the platform, the satellite data and the institute data. So many people, well, probably we don't think of it that way, but satellite is basically just an expensive computer that collects planetary data. But actually in most of the cases, that's the only way that we can collect this kind of data. So at the beginning, we have some engineers, scientists, they developed a satellite or instrument in a lab or laboratory setting. And then we send that satellite to the space orbiting some planet, in this case, Earth. So by the way, this satellite is called a SMAP. SMAP stands for soil moisture active positive, something like that. So what it does is measures soil moisture in Earth. So it was also developed in JPL and collects soil moisture related data. So now we got a satellite on the space. It takes some measurements. So eventually the data will be streamed back to Earth, where these kind of these big receiver dish. So we have a couple of these receiver positions around Earth. Together, they call the Deep Space Network, DSN. By the way, it's also managed by, the DSN is also managed by JPL. So also on the far hand side, that artwork is called Orbit Pavilion. That is a artwork created by some JPL artists, and it was showcased in Huntington Library for a couple of months. So what it does is, whenever a Earth orbits a satellite, go around us maybe go over Los Angeles. You can go on check. So you will play a sound corresponding to that satellite. So yeah, that's pretty interesting. I think we took it down last year or maybe 2 years ago. But if you are interested, you can still go on YouTube to check it out.
Is this your slide?
Yeah.
So let me just put it in. Just give it 1 moment. Sure.
Stop the sharing, stop sharing, resume the sharing.
Where do you have this?
Region.
So just change the screen to that screen. Now just go to the Zoom.
Okay. Oh, did you already?
No. So
Okay. It should be up there.
wait a minute.
So, okay, got it.
So that.
Okay, got you. Okay.
So the Zoom is showing that screen, so that should be fine.
Let me do it.
Just do the screen share, because the other thing, the screen share goes up.
Oh, okay.
So it's like still stuck on that first. Screen share is
It's over
pause.
here. Oh, it's very soft. But I got here.
Zoom share.
Share. I did. What's up, Rama?
Oh, you need that image, right? Yeah, otherwise we would just use the preview. So I don't have time. Don't do 2 screens, just do a single screen and then just share the entire screen.
Sorry,
Yeah, that's
yes. Should open now.
yeah, just do this one and we'll see the two.
Sure. Thank you. Okay.
So continue from last slide, the satellite captures some data, it sends back to the Earth. So you can imagine a satellite go around Earth and we capture what happens. You show like a picture of Earth at that moment in time. So when we send this raster image together along the time dimensions, we got an array image. So by the way, this is the data formats that scientists like to share Earth data. This is also called the level D data. And then so I talked about we ingest satellite data. We also ingest in situ data. So getting in situ data is actually quite cheaper and easier. So as you can see here, we have a instruments. These instruments are positioned on top of a JPL building. So what it does is it collects like 10 types of atmospheric pollutant data. And also, I believe the engineer told me that this is connected to the internet and it has its own API. So at any time, we can actually query this instrument for the data. So, so we have the satellite data, and it has a really a very wide coverage. So why do we need in situ data? So you might think. The reason is a satellite as we saw earlier, it does not stay on above our head all the time. It's actually kind of orbits Earth. So it probably takes a measurement like once a day, or maybe sometimes like once half a day. So by contrast, the in-situ instrument is they can collect far more data sets, pretty much continuous. They can take a measurement every minute or maybe like every seconds. So if you want to do a detailed study, we have to tap into in-situ data as well. So this is the framework that I talked about, the Analytic Collective Framework, ACF. So on the left-hand side, we have the in-situ data and the satellite data. So we ingest into that center box in the middle, the lack of better word. And then also what that does is ingest the data, kind of like partition it into a standard format. We store it in some sort of storage, and we also provide API endpoints for applications. So let me show you some of the applications that we have support. So in here, we support a lot of applications like this, but I do want to highlight some of the generic applications such as GIS and Jupyter Notebook. We are also able to support that. In here we have an application called the NASA Sea-Level Portal, and I want to show a short video of how it gets the data and how it renders it. Okay, so I guess it plays by itself. Cool. Yeah, so basically this is a very short recorded screen recording of the application. So as you can see, it's getting the time series data from the framework, and then it renders the image from here. So remember that that box that I talked about, in the middle, that stores data and that's all the API points and things like that. That is actually called Science Data Analytic Platform, SDAP stack. So this is actually we have been working on this for the last 10 years, and each year we add some more capability to it. And actually, at some point, at this point, we want to open source it as an Apache software. It's in incubator right now. It's completely open source. We plan to release it to Apache. Hopefully, this will become a useful tool for anyone who likes to study Earth-related data. Okay, so we talk about the SDAP, the box, the core framework. So AQACF, AQ stands for air quality. So obviously this is a adaptation of the framework of the SDAP for air quality research purpose. So actually in this project, actually what we do is we host some of the data into two places. Some of the data actually hosted in JPL, and another data, and then we have some other data sets. Kang was hosted in George Mason University, so it's on East Coast. So this is the first time we try to do that, because our tip on slicing the big data is not to store all the data in one place, but rather we allow it to be kind of scattered around. And also we only load satellite data and user data, as I said, it's they are really big, and there's so many of them. So we only just we only want to gather the data that we want to look at for each study. Okay, so here is a notebook example of how we Jupyter Notebook example of how we query the data and show a time series on on a Jupyter notebook. Also, we did some symbol visualization using the notebook. But I also want to show you that we can also plug this into a, okay, yeah, this is also a, we can also plug this into a high performing computer clusters to render, high definition, pictures. So this is one of them. And then, yeah, this is the high performing computing cluster that we use to basically generate this very high definition GeoTIFF. And that's pretty much about the framework. I only can provide a very high level view. Actually, the detail of the framework are broken down into different talks. But I do want to showcase some of the use case of this AQACF. For example, California have a electrical vehicle mandate by 2035. So we want to do some study like, okay, how will this benefit us? So two of the questions that we want to ask is, how does air pollution in California respond to changing vehicle emission? And what are the impact on human health and exposure? Also, how can air quality modeling data and remote sensing observation can be used to present answer to this type of question? Well, basically, just one question is like, how does it benefit? How does the air pollution make us healthier? So this research was actually done by I believe it was done by Colorado University. So what they so without getting into the details of what they do is they somehow found a formula, the causation between air pollutants and natural human deaths. So they figure out, okay, how much pollutants will contribute, how pollutants contribute to a natural death, how people die. So with this model, and oh, by the way, these are just to show some of the observations that they have, and the observation against the prediction. So with this model, so what happened is once they know that, then they can just associate that knowledge with the air quality data that we have. So we are able to figure out that, for example, if we reduce the PM2.5 from the transportation, we can actually reduce the 304 deaths in Los Angeles, and in Northern America, we are able to reduce 540 deaths annually. These are the annual figures. Another case we want to look at, recently there's a backlog at ports of LA and Long Beach. So we want to look at how that causes the pollution in Los Angeles. So I think this research is done by maybe Cal State LA. So basically they did some they gather some institute data from the Port of Los Angeles and correlate that with the satellite data, and they are able to find that the Los Angeles basin average PM 2.5 in November and December. As you can see, there is a spike in 2021. It's the highest all-time records. Well, that's because all the ships are kind of piled up in the port of Los Angeles and Long Beach. Yeah, this is basically a we also query all that data information into a Jupyter notebook. And I selected, these two study places for you guys because, it's related to Los Angeles. We have a couple one I did not show here. Particular one is quite interesting. This was developed by Cal State LA professor and his research team. So what he does is it's called predict what we breathe. So it's able to use air quality data to predict into the future, like how much pollution will be in the Los Angeles in the next 10 days. Yep. So that's it. That concludes my presentation. So you guys have any questions? Yes. Yeah, definitely a PM 2.5, and also those two are I see constantly, that has a very high correlation to health issues. Yeah, and I'm not a scientist in that area, but I see that that's being brought up all the time. Yeah, so button.
It's probably regarding the screen share.
Oh.
It's probably. Oh yeah. It's not forces. It's fine.
Okay. Yeah, I guess we cannot do much about it.
It's because of the software, so it's fine.
Yeah. So yeah.
I guess we're done. Thank you.
Thank you all for coming here. That was our last speaker for the day. I hope all of you will meet us at Boulevard for the closing ceremony. Thank you again to our speaker, Jason, for speaking on an interesting topic. And thank you again for your interesting questions and coming here today. Thank you.